Hi everyone, I'm Carlos Hinojosa and today I'm going to present our work on enhancing protection in face identification by using privacy-preserving optics. Traditionally, cameras are designed to capture images similar to human vision. Hence, the lenses are designed to minimize the aberration or defects on their surface so they can form a sharp image. In a traditional computer vision pipeline, the acquired images could be stored in a server dataset which is used to train machine learning models. This traditional computer vision pipeline is vulnerable to adversarial attacks. Among privacy-preserving solutions, face identification using generative adversarial networks provide effective balance between privacy-preserving and maintaining utility. However, current face identification methods operate at the software level. This creates a security gap between image acquisition and model training, as an attacker can intercept the image during the transmission. In this paper, we developed a hardware-level face identification approach to close the security gap. Unlike conventional cameras, our methods maximize lens aberration to produce highly degraded images, thereby enhancing privacy protection. However, we designed this distortion in such a way that face geometry features are preserved, enabling us to extract a reliable face heatmap. Some prior works on face identification proposed to use handcraft techniques such as blurring, masking, pixelation, and direct face replacement to protect the identity. On the other hand, face identification using generative adversarial networks provides a better privacy and utility trade-off than handcrafted approaches. However, both of these approaches are implemented at the software level. While they preserve privacy in the final application, they directly process the source image, which can expose potential privacy issues. In contrast, hardware-level approaches are considered more secure as they directly modify the optics, adding an extra layer of protection for sensitive data during image acquisition. Previous approaches in this category have used predefined optics to achieve anonymity by averaging a target face image with a display mask. Our proposed face identification framework combines the strength of game-based methods with optics learning. This approach aims to enhance privacy protection while preserving the utility of the images. Our framework consists of two main stages. In the first stage, we jointly optimize the camera optics and the heatmap regression network to obtain a face heatmap while ensuring privacy protection. This face heatmap allows us to infer global geometry information of the source image, such as head pose, position of eyes, nose, and mouth, without exposing the subject identity. In the second stage, our primary goal is to learn the parameters of a conditional GAN. This GAN generates a new face identity using the input privacy-preserving image, the face heatmap, and the reference image. Let's see stage 1 in details. Our optical system consists of a camera with two thin convex lenses and a face mask between them. We parameterize the face mask with Cerny polynomials where each polynomial describes a wavefront aberration. During the optimization, we learn the coefficient beta sub j. The face mask we learn modulates the light to produce visual distortion. In our training, to encourage image degradation, we minimize the difference of the acquired image Y with the original image X. Also, for easy and faster convergence, we promote symmetry and low frequency using a predefined defocus point spread function as a regularizer. At the same time, we optimize the face mask with a heatmap regression network to extract the face heatmap information. Our goal is to obtain a heat map from the privacy-preserving image that closely resembles the heat map derived from the original image. To achieve this, we incorporate this additional loss function. Overall, we fine-tune the camera model and the regression network end-to-end to gradually distort the optics and learn to extract the heat map from the privacy-preserving image using the following full objective function. Now, let's see the second stage. After training the lens face mask and the heat map regression network, we froze them and trained our generative network. In contrast to StarGAN, we train our discriminator with reference images to prevent filtering facial information from the source image during the optimization process. Overall, we now train our generative network using the following objectives, where the first four losses are adopted from StarGAN, while the last two losses are specifically proposed to improve the generation when using our privacy-preserving image. Specifically, we propose the LPIS loss to improve the generated image quality and more effectively reflect the reference image face attributes. And also, we propose a facial expression consistency loss to preserve small expressions like smiles, eyes blinking, or a small mouth movement in the generated image. We trained our proposed model on two well-used datasets, CVPR and FFHQ. To compare with other methods, we followed the common practice of using the FFHQ dataset for training and the CVPR dataset for evaluation. Following previous work, we evaluate the identity protection given by our face identification approach by measuring the L2 distance of embedding vectors from the identified and original faces extracted by pre-trained face recognition model. We further evaluate the utility of our generated images and the preservation of facial attributes from the source image by measuring the face landmarks, face bounding box, and the Frechet inception distance. Note that in general, we are interested in increasing the L2 distance while decreasing the other metrics as much as possible. Here we show some generated faces using our proposed framework. In the first row, we show the source images, which is the input of our privacy-preserving camera, and the second row shows the corresponding output. Our generative network generates new faces using the acquired privacy-preserving image and the different reference image shown in the first column. We conduct a series of experiments to investigate the contribution of the different losses. We observed that the inclusion of the facial expression consistency loss significantly improved all the metrics, especially the landmark, demonstrating their contribution to our framework for preserving detailing expression like smiles in the generated images. Also, the inclusion of the LPIPS loss generally improved the L2 distance metrics while preserving improvement in the other metrics. Here we compare our approach against state-of-the-art methods. We observe that our generated images have the style extracted from the reference images and face geometry of the source images. To further validate our method, we built a proof-of-concept optical system in our lab in Colombia. Here you can see the experimental setup where there are two cameras. The first camera acquires the images with distortion and the second camera acquires the images without distortion, which are used as ground truth. The main optical component which performs the distortion is the deformable mirror. Here we show some experimental results of the acquired privacy-preserving images with our camera implementation. Furthermore, we compare our approach against using low-resolution cameras. Thank you for your attention. Please visit our poster on Thursday, June 20. Feel free to download our code and visit our webpage.